Study Unit 1, Lecture 6. This lecture focuses on the insulated gate BJT or IGBJT, which combines the properties of FET devices as well as bipolar devices. So this device also has a collector and emitter, but instead of having a base, has an insulated gate. By combining the two devices, a device is achieved which has the high on and off states of the BJT, but the high gate insulation of the MOS. The IGBJT has a gate, an emitter, and a collector. The BJT structure can be seen here as having an N region, a P plus region, and at the emitter another N region. And then the channel which exists in the device is controlled by a gate over here. Functionally, the IGBJT works as follows. A voltage or positive voltage is applied to the gate. This induces a channel between the N regions at the emitter. This causes current to flow from this N region through into the collector from the emitter. This is also effectively the base injection current, which then causes current to flow from the emitter through the P region and into the collector. The advantage of this structure is the very high injection of minority carrier holes into the P region. This increasing conductivity in what is called the drift region significantly reduces the region's resistance, which allows the IGBJT to conduct very high currents. In the on state, the current through the IGBJT is given by the MOS current multiplied by 1 plus the current amplification factor of the PNP transistor, or rather 1 plus beta. If beta is very large, then this is approximately IMOS times beta. In order to turn the device off, the gate must be shorted to the emitter or pulled to a voltage which is below the threshold voltage of the MOSFET part of the transistor. By putting the gate to a negative voltage or tying it to the emitter causes the channel to cease to exist in this P plus region between the two N regions. Once this channel can no longer exist, there can no longer be carriers and the turn-off process begins. This turn-off, however, cannot happen quickly because there is a very high concentration of minority carriers in the N region. What this means is that as the gate is turned off, there is an initial decreasing current, after which there is a decay of current through the device. This decay of current is known as the tail current of the IGBJT. This turn-off behavior means that the IGBJT cannot switch as quickly as a traditional MOSFET device. In order to get around this, the IGBJT structure is often modified in order to optimize one or other performance parameter. Much like a PIN diode, the IBJT can have its doping profile structured in such a way to create preferred field strength profile through the device structure. The inclusion of an intrinsic buffer layer, much like the PIN diode, reduces the carrier lifetime in the FieldStar PT IGBJT. What this means is that by using this type of doping profile, these devices can switch faster than a conventional insulated gate BJT. As was said before, the current through the IGBJT is simply the MOS current multiplied by the beta of the PNP part of the transistor. This can be expanded as 1 over 1 minus alpha multiplied by the MOS current when the MOS part of the device operates in saturation. Finally, the forward transconductance of the IGBJT can be determined simply by differentiating the current with respect to the gate source voltage. If VDS is held constant, then the forward transconductance is simply 1 over alpha K prime N multiplied by W of L multiplied by VGS minus VT, since there is only one VGS in the equation.